This video presents an overview of the final demonstrator system developed within the DIOMEDES project. The demonstrator system features the user terminal that is connected to a 3D display and a 12 active loudspeaker setup. The pre-encoded video streams are stored within the content server that is residing at IRT in Munich. The DVB-T broadcast is done locally using the stream player on the screen. The PC equipped with the DVB-T transmitter is connected to the user terminal via cable. On the display, the user interface is seen. As a first step, all distinct modules running together in the user terminal are initiated. Those modules are the DVB-T receiver, synchronization buffer, peer-to-peer engine, adaptation decision engine, authentication module, and the decoder controller. In the second step, the list of available contents is downloaded from the content server at IRT. Upon the communication through the authentication module, the main seed server at IRT sends the list as seen on the display. Following the activation of the selected media, the chunks start to get downloaded from the main seed server and the other peers that have joined the same session. And in the third step, the DVB-T receiver is activated and starts buffering the incoming DVB-T streams. After the activation, the peer-to-peer engine is immediately updated with the current DVB-T clock and calculates the next chunks to download accordingly. The long red lines on the screen denote the skipped chunks in order to catch the DVB-T stream from the correct position. The video cluster that comprises 8 scalable video decoder instances and the multi-view depth renderer is distributed across 2 high-end PCs. 4 concurrently running scalable video decoder instances are shown on the PC's display. All decoders are fed by demultiplexed and decapsulated texture and depth streams. The decoded video frames are forwarded to the renderer that runs on the GPU of the second PC over an InfiniBand connection and using the TCP protocol. The 3D capable display on the screen shows all the decoded 8 streams side by side, which are the texture and the depth maps of the 4 cameras. The 2 of the texture streams are delivered through the DVB-T network, whereas the others are delivered from the seeder or the other peers on the network. The graphical user interface of the user terminal allows the users to navigate in the scene in between the allowed boundaries. To do so, 4 sliders have been provided. These can be used to shift the observed viewpoint in the horizontal direction, in the vertical direction, in the Z direction that is perpendicular to the 3D display. Users can also change the angle of the virtual camera by playing with the azimuth slider. The 5th slider allows the users to adjust the perceived depth by changing the baseline of the rendered virtual stereoscopic view. In order to show the adaptation behavior of the peer-to-peer engine under bandwidth throttling conditions, we have adjusted the total download capacity of the user such that the available bandwidth is only about 1/4 of the total content bitrate. This allows approximately 2 or 3 video-related streams to be downloaded by the user. The horizontal viewpoint shift slider is slided from the rightmost to the leftmost camera position. It is noted that in a very short time, the peer-to-peer engine starts downloading the chunks of the texture and depth of the leftmost camera. These are the lines that turn to green on top of the peer-to-peer window. The view on the display is recovered with minimum interruption. Subsequently, the horizontal viewpoint shift slider is slided from the leftmost towards the rightmost camera position and left around the center position. It is noted that this time the lower lines in the peer-to-peer window started turning to green, which corresponds to the rightmost camera. And then comes the enhancement layer stream for the center viewpoint. It is seen that the peer-to-peer engine attempts to adapt to the currently available bandwidth in a very short time based on the stream priority ranks it receives from the adaptation decision engine. In this part, the screenshot of the peer-to-peer engine running on the user terminal is seen. The hybrid delivery is active, where the vertical red line depicts the current time of the playback. 2 other peers in the network are also watching the same content, which are the bottom 2 lines. The topmost line corresponds to the main seed server. As can be seen, the majority of the currently downloaded chunks are scheduled from other peers rather than the server. These are marked with a red plus sign. Subsequently, in order to show the reaction of the peer-to-peer engine towards peer churns, we block the incoming chunk streams from the peers using a software bandwidth limiter. Accordingly, it is observed that the prospective chunks start to get scheduled from the main seed server, since the connection with the peers is regarded as lost. The red plus marks on the downloaded and buffered chunks disappear. On the other hand, the peer seamlessly continues to stream the 3D media chunks despite the churns.